I want to discuss compute the sequence of function in a point. So let's see how to do this computational seminar. And also last week, this session, we talked about some residues of some functions in a point, but I want to make more applications with this theory because it's very important and you will need it. So let's start by reminding what means singular point of a function. The classification of singular points would define the residue of function of pole of the so the the residue function is singular. Classification of singular points. So usually when you have a function f defined on D, which is a subset of C with values in C, and a point in C, then A is a single point which is removable if the limit when C goes to A from f of z is something finite. Then A is a singular point which is called a pole if limit when z goes to A from f of z is infinity, and here 1 over 0 means infinity, and actually if you have something which is not 0 over 0, it will give you also infinity. And A is an essential singular point, so it is essential, the singular point is essential. If when z goes to from Z doesn't exist. So a singular point could be removable, could be a pole, or essential. And I have told you that if A is a pole over the F, the residue of the function f in the point z equals A will be computed using the following formula. 1 over n minus 1 factorial times limit when z goes to A from z minus A at n times f of z, and this is a function for which you have to compute the swap derivative. So this is not well, which tells you for how many times you have to compute the derivative of this function. I'm going to write here that this is the order of the derivative. Oh, going to work in majority of time with false, but the removable point, the residue of that function in that point will be equal to 0. So if A is a removable singular point, zero of the function f in the point is equal to, okay. And now let's see some examples. In the first example, you have to find the singular points of a given function f and to compute the residues of f in each singular point. Let's see. Let f of z be the function given squared times e of z of z minus 1 times z squared plus 1. The singular points of a function are the points where the function is not well defined. Okay, so in order to find the singular points of f, you have to find the point where the function is. So in this case, having a fraction, the singular points will be given by equation in which the denominator is equal to 0. So from this equation, you have first that z minus 1 is 0, and z1 is 1, or z squared plus 1 is 0. So z2 is minus I, and z3 is I. And we want to find the singular points. So the aim is to find singular point of f. And we have them. And also, our aim was to find the residue of the function f in every singular point. Okay, and we want to find this residue. In order to find this residue, first of all, we have to find what type of singular points are z1, z2, and z3. So we have to compute the limit when z goes to z1 first from f of z. So this is the limit when z goes to 1 from z squared minus 1 times e of z of z minus times z squared plus 1. Oh, and now, if this is by 1, you will see that you have 0 over 0. So in this case, you should write this expression as a product. So this z squared minus 1 is actually z minus 1 times z plus 1 times e at z over z minus 1 times z squared plus 1. You simplify this fraction here, and you this equal to 2 times 1 is 2 times e over 1 plus 1 over 2. So it is e, which is something finite. This is a complex number. So it means that z1 is a removable singular point of. So for this reason, you have the residue of f of z in z equals z1 is equal to 0, because we have seen that if you have a removable singular point, then the residue of the function in that point is equal to 0. Oh, so this point is z. Okay, you have to when z goes to f of z, which is the limit when z goes to minus I from this function. You see that if you replace z by minus I, you'll have here minus 2 times e at minus I, which is something different from 0, over minus I minus 1, of course, times 0, because minus I was a root of this expression. So something which is not 0 get infinity. So in this case, 2 is a pole f. And I've told you that if you have such a case when the function which is above the fraction line is not 0 when you replace z by this pole, and this element is the root of a polynomial, which is the denominator of the fraction, then the order of this pole is given by the algebraic multiplicity of this solution. So if you take a look at this solution, you will see this solution is just one solution for z squared plus 1 equals 0. So it means that the order of this pole is 1. So in order to see better the fact that the order is 1, you should write this expression as a product in terms of z2 and z3. So it is z minus z2 times z minus z3, which is equal to z plus I times z minus I. So from this expression, you will use the order minus I is 1, because the exponent of this expression is 1. Okay, so you have that z2 equals minus I. From here is a pole of order 1. Okay, and this one is this. And if you want to compute the residue of the function f in point minus I, you have to use this formula with n equals 1 and a equals z2. So I'm going to write again this formula, but I will replace n by 1. So I have that the residue of this function f of z in z equals z2 is equal to, and we have here 1 over 1 minus 1 factor times the limit goes to z2, because this 2 is that a from the formula, from z minus z2 to the power 1 times the function f of z, and you have to compute the derivative of order 1 minus 1, which is actually the derivative of order 0. So from 1 over times the limit when it goes to z2 from z minus z2, this is 1, times f of z, which is z squared minus 1 times e at z over z minus 1 times z squared plus 1. And I've told you that this order is 0, so you don't have to compute the derivative of this function. But in this case, you have that this is the limit when z goes to z2, which is minus I, from z minus z2, so you z plus I, times z squared minus 1 times e at z over, and here instead of z squared minus 1, you could also write the simplified expression, which is z plus 2, because here when we compute the limit, we simplify this by z minus 1, so we get that the function is this one. So in order to be easier to find you should use this expression, which is z plus 1 times e at z over, and here you have z squared plus 1. But this z squared plus 1 must be written as a product in this way in order to have simplification between z side here and the plus I from here. So I'm writing z plus I times z minus this expression will be simplified. So minus I plus 1 times that minus I over minus I minus I. Okay, so it is minus I plus 1 times EL minus I could be let in this way, or you could write here cosine of minus 1 plus I times sine of minus 1 over minus 2I. Okay, and this is minus I plus 1 times sine of minus 1 I sine of 1, and this is minus 2I. So this is the first residue in a pole, and let's see the following singular point. So let's compute first the limit when z goes to z3 from f of z in order to find what type of point is this one, and then to compute the residue. So the limit when z goes to z3 from f of z is the limit when z goes to I from, I think it's the function without simplification. But in this question, actually not correct. You actually you have minus 2 times e at I over I minus 1 times, and this is 0 again, so the limit is infinity. And of course, you have that z3 is a pole, and in order to find the order of the pole, you have to get z squared plus 1 as a product. This is z minus z2 times z minus z3. So it is z plus I times I. And from the fact that the exponent from here is 1, you have that z3, which is I, is a pole of order 1. And again, we have to use this formula, but with z3 instead of z2, and to find the residue. Okay, so I want to find the residue of the function f of z when z equals z3, which no minus times v to z goes to v3 from z3 n, which is 1. Okay, so n is 1 times f of z, but in function f of z, I will write this expression. I have z plus 1 times e at z over z plus I times z minus I. Again, the order of the derivative is zero, so we don't want the and this 1 times is right. So this is minus I. So you have simplification of this one with this one. So you have limit when z goes to, instead of z3, I'm writing I, from z plus 1 e at z over z plus I, which is I plus 1 times e at I over 2I. Okay, and I'm letting this expression in this way. And this is it. Okay, if you have questions, please tell me. So this is the way in which you state which are the singular points of a function. And also, this is the way in which you find the residue of a function in a point. I've told you that you're going to work with poles, and this is why you have to know how to use this formula, which gives you the residue of a function in a point. It is not a formula, but you have to pay attention when you replace a and when you compute this derivative. Okay, and now tell me if you have questions, and if not, we'll see another example. Do you have questions?
No.
Oh, so if you don't have questions, let's move on. Let's say that f of z is the hyperbolic sine of a z of 2z squared minus 3 plus 3. Okay, let's say that this is the square. Again, we have to find singular points of f, and we have to compute the residue of function in single points. Let's start by finding the singular points, denoted here by SP. So when I'm trying to find these points, I'm actually solving the equation, the denominator equals 0. Okay, so from here I have that 2z squared minus z plus 2 equals 0. We compute it now with minus 4 times 4 here is minus 15. And so z1 is minus b plus square root of this one, but this one is actually 15i squared, so it is I square root of 15 over 2a, which is 4 in this case. And z2 is 1 minus I times square root of 15 over 4. Now, these are the singular points of f, and you have to find first what type of points are they, and then to find the residue of f. Let's start with z1. We have to compute the limit when z goes to z1 from f of z. And this is the limit when z goes to z1. I'm not going to replace z1 here because it's a long expression. From in h of z of but because of the fact that z1 is a solution for the denominator equals 0, it means that here you will have 0 because z1 was found in this way from this condition. When you replace z by z1, you will have a hyperbolic side which is computed in this value. This will be something which is not 0. So the conclusion is that the limit is infinity. And in this case, you have that z1 is a pole. But you have to find the order of this pole in order to find the residue. The order of the pole requires
Is it 2, the order?
yes, it's 2, because you have to write this expression of the product and the exponent for z minus z1, exactly. So this is equal to, let me write here, the fact that if you have an expression, let's say az squared plus bz plus c, then this expression is written in a product in this way. A minus times b. Okay, so z1 and z2 from here are the solutions to the equation. This one equals 0. Z are the solutions of az squared plus bz plus c equals 0. So in this case, if you want to write this expression as a product, you will have to write for this expression as a product using this formula. In your case, a is 2, so you have 2 times z minus z1 times z minus z2 all squared. Okay, from here. So it is equal to 4 times z1 squared times exactly. Okay, you were right. If you take a look at this exponent of z minus z1, which is 2, you will get that z1 is a pole of order 2. So the order of z1 is 2. Okay, and you have to use the formula that you've seen at the beginning, which is this one, with n equals 2 because n is the order, and instead of a, you put z1. So let's see how we apply this formula. We have that the residue of the function f in the point z1 is 1 over 2 minus 1 factorial times the pole from z minus the pole the power n, which is the order, which is 2, times the function f of z, which is hyperbolic sine over this expression, squared, times, so this times 1, and the order of the derivative will be 2 minus 1. If you have that residue is equal to the limit when z goes to 1, I'm going to replace z1 by this value because I have a lot of things to write. I'm going to work with z1 and z2 until I succeed to simplify here, and then when I compute the limit, I will replace z1 by this expression, but this will be in the end. And now, what you should do in order to have here, this denominator.
We applied the formula from before.
Exactly. You have to use the fact that this denominator is given actually by this expression. And I'm going to write here z minus z1 squared times hyperbolic sine of z over z squared times minus z1 squared times z minus z2 squared. This is the function. And to transform means I have to compute the derivative factor. And I have the limit when z goes to 1. You have a simplification here. Also, 1 over 4 is a constant. And know that if you have a constant times a function and you compute the derivative of this function, then the constant will come in front of the function and it will come in front of the limit too. So I'm going to write 1 over 4 times the limit when z goes to z1 from hyperbolic sine of z over z minus z2 squared. Now let's compute this derivative. You have a product here or fraction. So you can see this as a product or fraction as you want. If you see it as a product, you have to write it at times z minus z2 at minus 2 and to compute the derivative as a product. If not, you could compute the derivative of this function as a fraction. So this is the limit when z goes to z1 from, let's think about it as a fraction. So it's the derivative of the hyperbolic sine, which is hyperbolic cosine times z minus 2 squared minus this function times 2 squared, which will be computed, and you will have 2 times z minus z2 because this is u squared, and when you compute the derivative of u squared, you get 2u times the derivative of u, so this is u, okay, and you get 2u times the derivative of this one, which is 1 over z minus z2. Okay. You see that z minus here and also here. So simplification, you have here 3. And now I have to replace z by z1, so I have hyperbolic cosine of z1 times z1 minus z2 minus hyperbolic sine of z1 times 2 from here over z1 minus z2 cubed. And now you should replace one and zero. I'm not going to go anymore. So let's leave this expression this way. And of course, if you compute the limit when z goes to z2 from f of z, you will obtain again infinity, so 2 will be also a pole. And if you are looking here at this expression, you will see that also the order of z2 is 2. So similar, z2 will be a pole of order 2. And you have placed you you will a notation which is similar to this one, and this could be your homework. Okay, try to find the residue of this function in this point at home, individually. Okay. Do you have questions? Great. If you don't have questions, let's move to the residue theorem. You see that this theorem helps you find the value of integral here I, an integral which is computed on a closed contour, but only with circles, and this is why I write here the equation of a circle. So I have z minus z1 in module equals r from a function f of z dz. Okay, and my aim is to find the value of this r. I remind you that the module z minus 0 equals r is the equation of a circle centered in 0, but this is 0 is in the complex number, so it's x0 plus I times y0. So the center is the point x0, y0, and the radius is r. How do we compute this integral? We use the residue theorem. So I will write the theorem, but I will write the steps that you have to follow in order to find this integral. The first step consists of finding the singular points of the function f. So we find singular points of f. Step two is singular points of which found in the that is series of the domain bounded ones. So is given by this condition, modulo of z minus 0 less than r. This is the algebraic condition, but if you don't want to compute this module, you could draw this circle, and you could also represent the singular points of f, and from that picture you will be able to see if the points are or not domain delta. Step 3. We compute the residue of f of z in points from that. We the first have points we have, and then depending on the point, we put in the residual function f. And step I from the residue theorem is 2 pi times the sum of residues computed at step 3. And this is it. So you see that this theorem is very easy to be applied. You have a function, you have to obtain the singular points, to choose the points which are the interior of the domain bounded by the circle, which is this disk actually, to compute the residue, to sum, and to multiply it by 2 pi I. So in this case, the circle is this one. So if the circle has this equation, then the domain delta will be actually the interior of the circle. Okay, so delta is this one. The domain delta is this one, and this green contour is the so that's it. Okay, this is examples based on this theorem. Let's see. Using the residue theorem, compute the following integrals. Okay. Let's compute these integrals. Let's see the first. So we're going to follow this step. And the first step consists of finding the singular points of f. So we denote by f of z the function given here. And we found the singular points. As seen before, we must find the solutions of this equation. And solutions are z1 equals minus 2i and z2 equals 2i. So these are the singular points. But step 2, we have to find the points which are found in the interior of delta. Actually, in the interior of the domain bounded by the circle given here. So we have here two methods. Let's try to use both of them. First of all, let's use this method based on the algebraic condition of delta. If you have this equation, it means that you have a circle, and the here is given by modulo of z is less than 4. So I want to obtain the points which are in the interior of this disk. Let's see if z1 is in delta. In order to see this fact, we have to compute the module of z1, which is actually the module of minus 2i, which is equal to 2, because this is the module of minus 2 times the module of I. You know that this one is 0, the first one is 2, so it is 2, which is less than 4. So it means that you want to find out if 2 is delta, you have to compute the module of z2, which is the module of 2i, with the module of 2 times the module of I is 1, so this is 2, which is less than 4. So you have that z2 is also in that. I've told you that another method is based on drawing the circle and drawing data. So this is method 1. Okay, this is method 1. And this is method 2. And this is actually a symbol of center 0, because it is equivalent with z minus 0 plus 0i in module equals 4. So this is a circle of center 0, 0, and radius 4. Okay, so to circle, and I have to represent here minus 2i and 2i. 2i is here, and minus 2i is here. So you could see that these points are the interior of this. So you have to use the function f in each of these points. Now, let's do step 3. At step 3, we have to compute the residual function in all the points from delta. So let's take first z1 to see what type of point is this one, and then to find the residue. So step 3. We have to compare to this one from C, and this is the to told you that Z1 is minus 2i, okay? From this function. Okay, and here is 0, of course. And here you have something which is not 0. And you will see that the limit is infinity. So Z1 is a pole. And in order to find the order of the pole, you have to write Z2 plus 4, Z squared plus 4 as a product. So this is Z minus Z1 times Z times. And from the fact that exponent is 1, you get that Z1 is a pole of order 1. So Z1 is pole of order 1. And as you have seen before, the residue when equals 0 is actually the function when z equals minus 2. So the limit when z goes to minus 2i from z minus the residue, so you have z plus 2i at the power which is the order, which is 1, times the function. But here, I won't write z squared plus 4. I will write this expression. So I have z plus 2i times z minus 2i. You don't have to compute the derivative of this function because the order of the derivative is 0. So you have just the function. You simplification and minus 2i squared. Minus 2i squared or minus 1. Okay, which is 4. This 4 times I squared is minus 4 times 3 is minus 12 plus 1 over minus square I. And let's find the residue, but let's find first the limit. The limit when z goes to z2.
Wouldn't the limits for Z2 would be almost the same as Z1, but instead of a somewhere there's a plus, instead of a plus it's a minus?
Here to the residue, right?
No, for when we compute the limits for when
Z
Z
goes
tends to
to,
Z2, I
okay.
think I think the limits will be the same. I mean, Z2 will still be a pole of order 1. And the residue will be, I think, almost identical to Z equals Z equals Z1.
It's almost identical. Let me difference between them. Exactly, this is 0 here. This is something, okay, just let me copy the function. Let me copy the function. You have again 0 here. You have here something which is not 0. So again, z2 is a pole of f. It's right of denominator as that is a pole of the identical with z1. Pole of order 1. And let's see how this residue looks like. So when you have the residue, you have to compute the limit when z goes to 2I from z, which is 3z squared plus 1. See, I'm writing right. Or no, but I'm not writing directly. I have here z plus 2I times z minus 2I. Okay, and this function is multiplied by z minus this part, which is 2I, so the I think here. And 3 times 2 squared plus 1 over 4. And this will be a minus 4. Minus 4 times 3 plus 1 will be again minus 11, but here we have 4I, okay? So exactly, the difference is a minus. Okay, this was step 3, was very, very easy. Let's go to step 4. Uh, Step 4, because of computing the sum of the residues computed at step 3, and then the sum must be multiplied by 2 pi I. So in this case, I is 2 pi I times the first residue plus the second one. So this is, and with that, okay. Okay, if you don't have questions, then I'll let you, let's say, 10 minutes to find the value of this integral. Okay, to try to follow the same steps as I, and then we will discuss. I'm going to write in detail the solution, but first I will let you 10 minutes to think about it, and then we'll discuss and I'll write. Did you succeed to solve this problem? Have you tried to solve it? Have you tried to follow the steps to find the points to the points in design? Or still working?
Is the pole order for Z1 and Z2 1?
The pole of order 2, actually.
Oh, okay.
Okay, I'll let you 2 minutes to try to finish the solution and then we'll discuss. Okay, have you finished? So let's discuss. Let's see how you should solve this problem. I'm yeah. In this case, a function for is of squared plus 1 squared. Okay, for the first step, you had to find the singular points of f. The equation z squared plus 1 squared equals 0. You have that z squared plus 1 equals 0. So z1 is minus I and z2 is I. Then, at step
We see if they are in delta.
delta in this
And they are,
case,
I think.
exactly, delta in this case has the conditional modulo of z plus I is less than 5, not equal but less than 5. So let's take a look at z1. Is z1 in delta? We have to compute the modulo of z1 plus I, which is minus I plus I, which is I of 0, which is 0, and 0 is than 5. So this is in delta, exactly. Again, for z2, we have to compute a module, this time of z2 plus I. which is the module of I plus I, which is the module of 2I, which is 2, which is less than 5. So Z2 is also inductive. But step 3, we have to find what points are Z1 and Z2. So we have to compute the limit when Z goes to Z1 from f of Z, which is the limit when Z goes to minus I from 1 over Z squared plus squared. And this is from 0 to 0. Also, the limit when Z goes to Z2 from f of Z is infinity. So we have that Z1 and Z2 are poles of f, and in order to find their order, we have to write the denominator, which is Z squared plus 1 squared, as a product. You know that Z squared plus 1 is Z minus I times Z plus I, but here everything is squared because of this exponent. So it is Z minus I squared times Z plus I squared. Okay, so this is the denominator. You put from this expression, the order of I and the order of minus I are equal to 2. So Z1 and Z2 will be poles of order 2 of f. Okay, because of f, because of these values. Okay. To we have to use the and it gives everything to for each of the points. You have that the residue of the function f of z in z equals minus I is the limit when z goes to minus I from. You know that you have 1 over 1 factor in front of it, which is 1. I didn't write this because I'm trying to write the important part. So I have z minus the pole, so it is z minus this one, so it is z plus I, everything squared, okay, because I have to put there the order, which is 2, times the function f of z. But this should write 1 over this expression. So I have 1 squared times z minus I squared. And because the order of this pole is 2, I have to compute the first derivative of this function. I have here a simplification, and this expression could be written as z minus I at the power minus 2. And the derivative of this function is minus 2 times z minus I at minus 3 times the derivative of z minus I. So 2 minus 2 times I it's minus I, so I have minus 2 at minus 3. So it is minus 2 over minus 2I at the power 3, which is minus 2 over This is minus 8 times I cubed, but cubed is minus I. Have a minus from here, 1 over 4I. And this is the first residue. Okay, the first residue has this value, and let's find the residue of what equals I. So you have the limit when z goes to I from z minus the pole, which is I, the order of the pole, which is 2, times the function, which will also be written in this way. And again, you have to compute the derivative, the first derivative of this function. This is 2 naught minus 2. Let me write simplification. So we have when z I from z plus I at minus 2, and you have to compute the derivative, which is limit when z goes to I from minus 2 times z plus I at minus 3 times 1, which is the derivative of this, which is minus 2 over 2I at the power 3, which is minus 2 over 8 times minus I, which is 1 over 4I. Okay, so this residue is 1 over 4I. And at step 4, let me write step 4. You have to compute the sum of this residue.
It's 0.
Yes, it's 0. And to multiply it with 2 pi I, but it will be 0. And this is the value of the integral. And this is it. Okay, what had difficulties in solving this problem? Okay, let's see another exercise. Let's see the point C. This 10 minutes and this okay, that can to fit 10 minutes. So, succeeded to solve point C? Let's take a look at the solution of the point C. Let's denote by I this integral, and let's denote by f of z the function. Go to step 1. To find singular points of f, and let's find them by solving this equation, from which you have z squared minus 5z equals 3. And from here you have z times z minus 5 equals 0. So you have two solutions, z1 which is 0 and z2 which is 5. Then, step 2. We have to take a look at delta. In this case, is modulo of z less than 1. And let's check if z1 is in delta by computing the module of z1. This is the module of 0, which is 0, which is less than 1. So z1 is module z2 is the module of 5, which is 5, which is greater than 1. So z2 is not in delta. It means that we have to take into consideration only z1 because just this point is in delta. At step 3, we have to find out what type of point, and this is why when t goes to z1 from f of z, which is actually the when z goes to 0 from cosine of z over this expression. And this is cosine of 0 over 0, so it is 1 over 0 is infinity, so it implies 0. And we have to write this expression as a product. So this could be written as z times z minus 5, everything squared, which is z squared times z minus 5 squared. And from this fact, you have that z1 equals 0 is a pole of order 2. Because you're sorry. I'm sorry. Now you have to find the residuum of f of z in z equals 0. And this residue I'm going to write here is the limit when z goes to 0 from z minus 2 because this point times the function which is cosine of z over, but instead of this expression, I'll write this one. So it is z squared times z minus 5 squared. And you have to compute the derivative of this expression. This is actually z squared, which will be simplified with this one. And you have to put the goes to 0. So z minus 5 squared. And let's see. limit when z goes to 0 from. We will have the derivative of this one, the derivative of the cosine, which is minus sine of z, okay, times z minus 5 squared, which is copied, minus cosine of z times the derivative of this function, which is 2 times z minus 5 over z minus 5 to the power 4. Use simplification here, this one with this one with this one, and replacing z by 0, you get minus sine of 0 times minus 5 minus 2 times cosine of 0 over 0 minus 5 cubed. You know that sine of 0 is 0, cosine of 0 is 1, so you get minus 2 over minus 125. Okay, so it is 2 over 125. This is the residue, and now we are going to step 1 and to find the value of I using the formula 2 pi I times the sum of the residues, but in this case I have just a point which is in the interior of the delta, so I don't have to write a sum here, I just have to write the residue of the function f in z equals 0, and this is pi times 2 over 2. So it is 4 pi over 125, and this is it. This is the value of the integral. Okay, let's see another exercise. So this was the first exercise. Now the task is the same, but we'll have different functions. So exercise 2, find I equals the integral, which will be computed from the following function, z minus 2 cubed, and the function is z times e at z, dz, and the domain is module of z equals 5. Okay, I will let you 5 minutes to try to solve this problem, and then we'll discuss. Have you found the result? Have you succeeded in computing? Okay, let's see. So first we have to consider the function which is denoted by f of z and is represented by z times e at z over z minus 2 cubed. But step 1, we have to find the singular points of f. And in this case, it's very simple because you have z minus 2 cubed equals 0. So you have that z equals 2. You have just z1, which is 2. Then, but step 2, you have to find the condition of delta, which is taken from here, but you have to put less than instead of equal to. And if you want to see if z1 is in delta, then you have to compute the modulo of z1, which is the modulo of 2, which is 2, which is less than 5. So it is less than 1. So that's point. But first, what type of point is z1? And this is why we are computing the limit when z goes to z1 from f of z. Okay, so this is the limit when z goes to 2 from z times e at z of to, and this is 2 times e at 2 over 0, which is infinity. So z1 equals 2 is a pole. It is very, very simple to see the order of the pole because you have here this exponent, which is 3. So it means that 2 is pole of order 3. Okay, so we have actually that z1 equals 2 is pole of order 3. And why for the residue, you have to compute the second derivative of that function. Let's see the residue. It is 1 over 3 minus 1 factorial. This time I'm writing this fraction because it is different from 1 times the limit when z goes to 2 from z minus the pole, which is 2, the power n, which is 3. So n is 3 in that formula, times the function, which is z times e at z over z minus 2 cubed. And this expression is a function for which you have to compute the derivative for the 2. But here you have simplification. And this is 2 times z goes to 2 from z times e at z. And you have to take the derivative of this function. So it is 1 times the limit when z goes to 2 from, we have to compute the derivative of this expression as a product first. So it is the derivative of this function, which is 1. So we have e at z plus z times the derivative of this function e at z. But again, you have to compute another derivative. And to be easier, you could write this expression as a product. So you have e at z times 1 plus z, and you take the derivative of this function. So you have 1 over 2 times the limit when z goes to 2 from it, the derivative of this one, which is the same, times the second function, which won't be changed, plus this function, which is copied, times the derivative of this function, okay, which is 1. So we have 1 over 2 times the limit when z goes to 2 from e times 1 plus e z, which is times e at 2 times 3 plus e at 2, so it's 4e at 4e squared over 2, so it's 2e squared. Okay, so this is the residue. The residue is 2e squared. And let's move to step 4. And let's have that I is actually 2 pi I times the residue of the function in this point, which is 2 pi I times 2e squared, okay? 4 pi e squared times I. Oh, I understood what we worked today. If you have questions, please tell me. And if you don't have questions, please just wait a second to download the meeting attendance list. To check the attendance list also. Oh, just uh, are you here?
Yes.
Okay, I see that Anna left. Udre Alberto? Maybe you cannot hear me. Dragota Andrei, I have talked to you.
I'm
So
here.
It's yeah. George?
Prezident, merge microfonul.
Okay.
I'm here. I just.
Okay. Okay, it's fine. And Votorescu Vlad?
Yes, I'm here. I had some connection problems. That's why I joined,
Oh,
then
okay,
left,
it's
then
fine.
joined
It's
again.
fine. It's fine. It's fine. Do you have questions? Okay, if you don't have questions, thank you. Have a nice evening and good luck with part exam tomorrow.
Thank you.
Seară bună.
Thank you. Good evening.
Bye.
Thank you very much. Have a nice evening.
Have a nice
Nice
evening.
evening.